All right, I want to address one quick question here with respect to problem two, because I'm getting various different questions about it. I sense that people don't understand it. I uploaded the notes that address the particular questions in detail. Actually, if you want to derive how to calculate the energies and forces, I do that there in those notes. But basically, what's going on here, there's three things that it asks you to do. What it's basically saying is this yoke here has a weight of basically a force of its weight, all right, mg, that is holding it down. That apparently is 50,000 newtons, all right? So if I think of a free body diagram from physics, there's a downward force of gravity of 50,000 newtons. The action of the force of the field, which is the partial derivative of energy, and I'll say in the y direction, all right? What we're saying is the gap G can change. That would naturally be an upward force because what we said is the action is always to minimize the reluctance. Well, minimizing the reluctance would mean that it would try to slam G shut. So basically what it's saying is you ultimately, if I go through this process, I'm going to end up that this becomes 1/2 I squared times the derivative of L with respect to G. All right, that's effectively what I'm going to come up with when I go through this process. If you go through this whole thing, you're going to see that this should be some expression, some constant times Ni squared. And what I'm asking you for is to solve for what Ni needs to be such that the net force is equal to 0. And the net force would be basically a force upward, Fy, this guy, and the 50,000 downward, right? So the first part of that problem basically says if this guy is centered, right, where he's shown right there, what is the MMF that's required to do that? The second part of the problem is basically asking you the same thing, except what it's saying is, what happens if this guy were to move in that direction or the other direction? In other words, in those cases, these areas of overlap would be different, okay? And so what it's saying is what MMF would be required still if I want to maintain this condition. I don't want this thing to move up or down. All right. It's going to be different. Whatever MMF you solve for in the first part of the problem, you're going to need more if this thing moves to the left or the right. In the last part of the problem, it says, well, it's also the case that there's an X direction force, which would be the partial derivative of the energy with respect to X. The nice thing about that force is there is no applied force in this case. In other words, there's no force in the X direction, right? So unlike in the case of the first part, right? There's a force of the weight of this thing that you're dealing with. In the X direction, there isn't another force. And the good thing about this one is it's restorative. It actually works to, if the object for some reason is to move to the left, the force will be in the negative direction, meaning it will act to close it. Because the minimum reluctance condition is where this guy is perfectly centered, like he is in this picture. All right, so I'm going to stop there, but I think that should be enough, hopefully, for you guys to figure out how to approach that problem. The key thing is that for the second part, right, what you have to do is you have a vector x that you are given in the second part, and you have to solve for Ni at each of those values of x. In the third part, you're basically saying your force is going to effectively be a function of Ni, because the value of Ni that's required is effectively fixed by whatever I got in part 2. All right, so you're basically finding that the force is going to be different at each position, because the force that would be the MMF that's required to keep this thing vertically placed was determined in part 2. Okay. All right. Questions about that? All right. I suspect there will be. If you have more questions about it, you guys can ding me in Discord and we can address those. Okay. All right. The main thing I wanted to be able to do is to address something like problem 3 and what you're going to have on homework 8, which would be, what happens when I have multiple windings like I do here. So I wanted to take some time just to make sure that we were really on the same page with all of these sort of different issues about having multiple poles and all of that. Okay. So let's say I have this situation. So this is a cross-sectional cut of a cylindrical machine where the rotor can move. So the rotor is the middle part, stator is the outer part. The mu of this stator is infinite, and the mu of this guy is infinite. Okay. Now, what we're doing here is to keep things simple, I say let's put a DC current into coil A and into coil F. All right. And so if we just look at coil A, what I do is I go around the coil using the right-hand rule to figure out what the flux is going to do. And we've talked about this a number of different times, but basically what it's like is if the mu is infinite in the iron, so the mu is infinite here and here, then if I think of draw a magnetic circuit around this pathway right here, that magnetic circuit would look something like this. If there's N turns, there would be, and I say specifically for the stator windings that they have N sub S turns, there'd be an MMF that's N sub S times IA, and there's basically a reluctance of the two different parts of the air gap. So there's a reluctance here and a reluctance here. So it would look something like what I've shown right here. All right. Now this is a bit of an approximation. We don't typically use magnetic circuit analysis when I have a cylindrical setup like this. All right. What we do is we kind of go back to what are the original B fields. And we really only worry about this if we're designing machines. In this type of a class, we're really worried about just understanding how they operate. So to do that, I want to make sure that we, kind of understand exactly what's going to happen in these different cases. So I just real quick, I want to draw here what the field ultimately looks like. I think I wanted to put that slide. Oh, my slides are moving very slowly on me here.
Yeah.
Hang on. Do you guys still hear me?
Yes, we still hear you.
Okay. All right, good. I don't know why my stuff is moving slow on me. Okay. All right. What I want to make sure here is when I look at this setup, I want to be able to show what the B field looks like as a function of angle, right? And so I have my theta here. All right. So what I've shown is from theta equal to 0 to 90 degrees to 180 and 270 as I go around. The thing that happens in this particular case, I'm going to move all that stuff out of the way, is if I followed the field lines, say for this coil A, right, where his field would go in a counterclockwise direction, what's going to happen is the field is going to be purely in the radial direction, moving from the stator to the rotor on the left side of the stator. And on the right side, it's going to move from the rotor to the stator. Okay. Like that. So if that's the case, what I do is I say that from 90 degrees going around to 270 degrees, that my field is going in the negative radial direction. All right. So from 90 degrees to 270, this would be 90. This would be 270. My field's going in the negative radial direction. And then basically from 270 over to 90, okay, it's going in the positive radial direction. All right. And coil A is basically, this would be, this location here is where the dot is, and this is where the X is on coil A. All right. That's the alignment of coil A associated with that. And what we typically say is that where this field is centered, I call this the A axis. All right, where that field is centered in a period. Now, I'm going to talk more about that as I go through here today, but I wanted to start there. Okay. Now, the thing about this thing is what I have two different coils in this setup. I have a coil F on the rotor, and a coil A on the stator. If I have two coils like that, all right, so let's say I had two identical coils. All right, we can talk about their mutual flux, and I want to see if we can just understand the mutual flux. What I've done here is I've basically put the axis for the two fields. All right, so this would be my B coil, and this is my A coil. And I'm putting the same current into both of them so that basically their fields point in the same direction. All right, so if I'm talking about, let's say lambda AB, all right, so this would be, or maybe do it this way, BA. So basically the flux linking coil B from coil A, right? The way that I ultimately can think about that is it's the number of turns in coil B times the area of coil B times whatever the B field is from the other one, all right? So let's say the B field from coil A, and it ends up being times the cosine of the angle between those two axes. So theta R is what I'm defining as the angle between these two axes. If I look at what I've drawn for the A axis and the B axis here, what is that value in this particular case? What is the value of the angle between this axis and this axis? What number would you give that in this particular case? What's the angle between those?
120.
What's the angle in the picture that I've drawn right there between A and B?
180
They're
or 0.
They're perfectly aligned with each other, right? So we'd say that 0 degrees. In other words, both of those two arrows point in the same direction. If they both point in the same direction, the angle between them would be 0. Okay. Now, if I'm talking about A coil and B coil in a machine, they would be fixed 120 degrees apart from each other. But in this particular picture, those two axes are aligned with each other. In other words, I'm saying what's the angle between them? So I see the A axis in this picture is pointing at, so I guess is pointing at 270. The B axis is pointing at 270. So the angle between them is 0. All right. What about in this particular picture? What would I say here? What's
90.
theta R? Yeah, theta R is now basically 90 degrees. All right. So the flux from or in B from A works out to be N times the area times whatever the B field is times the cosine of 90 degrees. What's that equal to in this particular case? How much flux is linking in through coil B from A?
Would it just be NAB?
Well,
The number of turns the area of the magnetic field.
Basically what we're saying is that on net, this is the whole concept of flux. You're saying what's the total amount of flux that's passing through it? If all the flux is basically passing in this direction, on net, there's no net flux passing through coil B. And so I just plug in the 90 degrees, it's equal to 0 at that point. All right. So what we say is that it's 0 because no flux from A is passing through B. Now, in this particular case, the angle between those two axes is what?
180.
180, right? And if I look at it, the total net flux passing through B from A is the same, except it's oriented 180 degrees away from each other. So if I say lambda BA, it would be N times A times whatever the B field is, times the cosine of 180, which ends up being the opposite of what I had at 0 degrees. All right, this is going to be negative NA times BA. And what happens when it's at 270 degrees? What's it going to be in this case? What's the angle between the two? The angle between the two is 90 degrees again, right? Or if I'm real careful about it, it's 270 degrees. What's that make the mean, just looking at the picture, it's not that hard to think about it. If I've got flux from A that's going the direction that it is past coil B, what's the total amount of B field that's going into coil B?
Zero?
Zero, right? And in this particular case, it's essentially N times A times B times the cosine of theta R, where theta R is 270 degrees, like so. All right. So that is essentially the way this guy works. But the thing that's kind of important to me for a second is we know that a lambda is always equal to an L times an I. All right. So this argument's not too hard to follow, but if I look at this, N and A are constants. B field is always going to be some constants times the current. So essentially what this becomes is a bunch of constants. All right. A bunch of constants, which I just write as M. All right. Times whatever the current is, times the cosine of the angle between those two things. All right. So basically this is the flux linkage, the mutual flux linkage between the two. Some constant times a current times this guy. All right. And so we're going to use that later. All right. We've used it before, but I want to make sure that it's really clear so you guys can get through the third problem there on the homework. All right. So that concept's important, and I'm going to get to applying that when I have multiple poles. All right. All right. So if I have, hang on for a second, guys. It's not showing what I gotta escape from here. For some reason, it's not showing my slides properly here. And I don't know why. I'm gonna stop